Hello, everyone. As you start to join in, we're just going to wait for a couple of minutes while the attendees numbers comes up a bit, and we will kick off. So welcome. All right, so maybe we'll kick off. Welcome everyone to the first lecture in what is truly to be a cracking lecture series this semester. And it will maybe a nice way to end a very challenging year on computation and architecture. So the lecture series essentially has been put together by myself, Dr. Tim Schork, and David Pigram from the University of Technology, Sydney. And we've put this series together to help bring experts from around the world to really discuss very important topics that are close to our hearts as educators, but as well as topics that we're currently addressing and are asking our students in specific to address in our own little studios here at the university. As you can see from the list here, the lecture series is going to look at the application of architecture and optimization in design at various scales, whether it was the building, the city, or even in engineering. And so we're very excited to really bring this series to you, and hopefully you will find it very exciting too. So before I move on, I'll just let my colleagues, David and Tim, introduce themselves. So David, over to you.
Hey, I'm Dave Pigram. I teach in the School of Architecture. Of course, I think most people here will know me, and I'm extremely excited to hear PC speak today.
Great. Tim, are you there?
I'm here, yes. Hello,
Hi,
everyone. So yes, wonderful to kick off today. I'm looking forward to PC's talk, and I just also would like to acknowledge the, custodians of country, because it's about knowledge exchange, and also thank Mohammed for putting this together, and acknowledge all elders past, present, and emerging. And
Great.
Can't wait to see what we're being treated in for.
Super, thanks very much, Tim. Right, so now to introduce the star of the hour. So PC Thomas. So today's lecture is going to discuss, or is titled, Using Energy Simulations to Drive Design Decisions in the Built Environment. Essentially, the lecture is going to explore the use of modern suite of building simulation tools applied to drive design decisions for residential renovation in Eastern Sydney. So if you're from Sydney, if you're logging in from Sydney, that's going to be great for you. If not, well, get a sneak peek of what's happening in Sydney. So just a little intro for PC. PC Thomas is a director at Team Catalyst, an adjunct associate professor at the University of Sydney. He is a specialist in improving the energy efficiency and therefore reducing the greenhouse gas footprint of large buildings. PC specializes in integrated building design, using simulation tools to assist in the design and delivery of sustainable buildings, in particular in predicting the performance of the mechanical services. So PC, thank you very much for joining. I know Tuesdays 5 p.m. is not the best time for holding a lecture, but this time we can get as many people from all over the world as we can. So we really appreciate your time for this. So today's lecture is going to span about 45 minutes, and then we'll have 15 minutes at the end for discussions. If anyone has any questions, please start shooting them in the Q&A, and we will address them at the end. So don't wait until the end. As soon as you get a question, shoot it in, and we'll ask PC to kind of address those questions. So without further ado, PC, Makki, over to you.
Thanks, Mohammed, Dave, Tim. Thank you for the opportunity. And I'd say maybe reserve your judgment on the cracking lecture till it's over. Anyway, I should say that what I'm going to talk about today is actually not large buildings, but residential scale buildings, because they're actually much harder to model than bigger buildings. And I thought I'd start off with a bit of rambling. You know, if you're invited to do a lecture, you're given permission to ramble. So I thought it's a good time to start. And the way to sort of, the reason I wanted to kind of talk about that is because all kinds of analysis in buildings has a lot of mathematics attached to it, you know, and we forget sometimes how much math is going on behind the scenes. And then when we use models, you know, there's, you can talk about lots of simple models, like they can do one thing very well, like heat flow or air flow or daylight or looking at building fabric or whatever. But when you start to look at the integrated performance of a building from many aspects, then you'll start to find that the number of models start to reduce, right? You only get a handful of models which will do an integrated thermal performance type assessment in the world, right? So to give you and these models, of course, change in time as information becomes available. And I thought I'd give you an example using how models have progressed in cooling load calculations for air conditioning, right? And one of the reasons is it actually is quite new, if you think about it. You know, the first models that became available were 1927, a guy called Carrier came up with this way of making a building cool. And essentially he did it to dehumidify printing presses, not even for comfort. But he didn't really have much maths. It was really observational stuff. You know, okay, the sun is coming in through here, heat is flowing from here to here, what shall I do, you know? And it took 40 years for us to get models which actually started to account for the thermal response of mass in buildings. If you have a wall and there is a temperature on the inside and a temperature on the outside, there is a response. It stores some heat and it releases some heat. And it took the fast Fourier transforms to give us a whole series of updates. That was a big jump in that calculation process. But it took till the end of the 1990s to actually start looking at not only storage and in the release of heat from opaque materials, but to accurately account for data of solar radiation coming in through the windows, the transparent part of the building envelope. We used to use a fudge called solar temperature till that time. We still do sometimes, right? Anyway, so it's easy, you know, something to remember as we start to look at some of the stuff that we're going to do today. And because they're so complicated, I have this thing that I try to use models that are in the public domain, that are well tested, well documented, hundreds of PhDs input into them. The documentation's available transparently, and a couple of them I use are on the screen. There's Energy Plus for thermal simulation, Radiance for daylighting.
Can I just confirm that you're sharing your screen?
Hang on, let me go back and see. Sorry. I'm just finding my Zoom, hold on.
It's all right.
Here we are. I'd forgotten I'd stopped sharing. All right, you'll see a blank screen right now.
We
I
see your
think we
desktop.
just see your desktop. Yeah. Now we see it. Yeah.
Perfect. So I just go through, I've just talked to these slides and yeah, there you go. So I was saying that, that's why I choose to use public domain software, because they're well documented. And two of the models I use a lot are given there. Energy Plus for thermal simulation and radiance for daylighting. And you can search them on the internet. You'll find, a lot about it. So why am I doing this ramble? Well, to kind of say that when you use a model, understand your domain knowledge first. If you're using thermal performance, learn building physics, and then use your model to test your design. Don't let the model drive your design, right? And the other thing I think most people who do models will agree with me is, remember, as the Irish say, shite in equals shite out. If your model is not a reasonable representation of what you're trying to analyze, your results are pretty much worthless. Okay. Having said that, let's get into the the lecture. We're looking at Sydney. So here's a kind of summary of weather data from a model called Climate Consultant. You'll find it. There's not much I wanted to say, except to say that, in Australia, we have wicked climates, moderate climates. So we have a heating season, and we have a cooling season, and we have a middle season where if you do it right, you don't need much heating and cooling to be comfortable. So I'm going to talk to you about a renovation we did on our house on a 1930s kind of cavity brick semi. It's a building, double brick, very typical of Sydney's eastern areas, and located on a very standard suburban street, and like most semis, a long plot, right? And basically this faces north, that faces south. So my garden faces south, if you wish. And here's a picture before we did the renovation. So if you look carefully, you can see this thing was jerry built in the 1970s as an add-on on the main house. And if you look carefully here, you can see there's mold beginning to appear there. So, it got to the point where we had to kind of decide to do it or else. Buildings and renovations are not the easiest times in your life. But anyway, so step one is to do a design. And we had a design in mind. Lena Thomas, who's professor at UTS, did the concept, and Peter did the drawings for the detail. Now I'll come back and we'll look at this again. There are a few elements that I want to talk to you about specifically, but let's keep moving for the present. So we built a thermal model, right? And I want to impress upon you that this is not a CAD model, it's a thermal model. So there's a fair number of things that it brings with it. It's a database with all kinds of things. And the way this model was built, there's a neighbor's house next door. And then our semi is this one here with all the windows on it. And the semi that's attached to it is over there, right? Now, what I wanted to show you was that in this model, we're going to look at this renovated bit. And so a lot of the stuff that I'm going to show you is going to be on that. And then if you look at the representation of that model over here, it's the living room on the ground floor. And I'd particularly like you to look at this last element here. So that's the wall that faces west, and it has two windows on it, these two windows over here. And the bits that are in purple, they're really modeled as a shading device. They're not really modeled as a thermal performance part of the building. Now, these models were built almost 5 years ago. If I was rebuilding these models, they would be different. This would no longer be a whole model. It'll probably come out in pink because all I need is its shading impact on my building. The one that's the semi next to mine, I would have built that as an adiabatic model because I don't really want to know much about the heat transfer between them since that part is kind of insulated from the other. Okay, having built this model, I want to use it to do some design decisions. I want to make some decisions based on that. So one of the first things we did was to kind of look at how does light play out in our design, okay? So if you look at this model, this is a what we call a static analysis done for an overcast sky. What are the daylighting levels inside the building, inside the rooms? Obviously, you've got the old part of the house, 1930s, and you can see here fairly dark everywhere, except very near the windows. The new part that we're proposing has got much more daylight in it, okay? Now, how do I use this to take any sort of decisions? Well, we were extending the kitchen, and if you look at the kitchen, you can see that one half of the kitchen near the window has some daylight, but this part of the kitchen was fairly dark, you know, and that's something that there was the opportunity to put some interventions. So obviously that much was enough for me to take a decision. I mean, we could have done much more analysis, but at that point we said, right, what we need is a solar tube or a skylight, which brings in daylight in the kitchen. And that's what it looks like after it was built. Now, recently we went back and did a second model, something that wasn't available at the time when we did these analyses, to look at, well, what can we say about daylight across the year rather than at that one point in time for an overcast sky. So now you've got a way of looking at useful daylight and how you can utilize it. So what you can do is you can put a range. So the range that I've used here is between 100 lux and 3000 lux. And it cycles through every hour where daylight is available, and then it works out the number of hours when daylight is within that range. So if I'm looking at that range, I'm going, wherever it's dark, wherever it's blue, then there's less percentage of the time that that building is, that space has got useful daylight. And you can see here that, you know, near those big windows, you get about 50% of useful daylight, but between the windows, you're getting a lot of useful daylight. You know, and that sort of analysis starts to give you some ideas as well. And you can see that my kitchen decision, had I been able to do that, would still have given me some indication that there was too little daylight here. Now, compared to what was happening with the overcast sky, you can see here that while there's a lot of daylight close to the window, actually I've got a fair bit of usable daylight, even a little bit lower, deeper into those rooms. So that's kind of a thing that we would do with daylight. Now, the next couple of things are, I was interested in, you know, what's the performance in winter and summer? So the first thing I did was to kind of put a visualization of the sun interaction with the model. This is on a winter morning. I think it's 9:30 on the 21st of May that you can see here. And there was a particular reason that I was looking at these models. I mean, we can dynamically move the sun and get a movie and all that sort of stuff. But literally what I was interested in was, in the morning, how much sun am I going to get through this east face, which is facing the neighbor. And that's the morning sun. You can see there's a patch of sunlight on the floor there, 9:30 on May the 21st. And there's a reason for doing that. And that's because after it was constructed, I took a picture at 9:30 on the 21st of May, and there's my sun patch. You know, it sort of gave us a lot of confidence about our models. You can see the patch there, and you can see what it looks like after. But the reason I did that analysis was actually trying to figure out how many hours of sunlight would I get on a winter day. And what it turns out is that I get a couple of hours in the afternoon of useful daylight. I get 1 to 1.5 hours of useful daylight in the morning, but the rest of the time, the two roof ridges, our own roof ridge and the neighbor's roof ridge, actually cut away the solar radiation. So I get some sunshine, I don't get a whole lot, okay? And the models bore it out. So I took an afternoon picture. That patch is a bit smaller than in the model because I've got a curtain across that window, but otherwise it's pretty accurate. Anyway, with that, what the decision is, you know, you're going to have trouble in the winter. You don't really have too much solar gain coming in through the windows. So the design decision obviously is to insulate. So insulation on the floor, insulation on the walls, insulation on the roof. Now, we had to think about how we did that insulation. Okay, and here are some drawings that Peter made for us after we had some discussion about that. If you look at the roof insulation, you can see this aluminum foil over there. Okay, and then you can see this beam, and you can see there's a bit of a gap before the next layer of insulation in between the beams. And there was a reason for doing that. And that is because if you have aluminum foil, it's a non-permeable, non-vapor permeable membrane. And it's possible that you could get condensation on that membrane when the temperature differentials are high, like in a winter night. If you're warming up the room from the inside and the roof is facing a cold outside, it's possible to have condensation. So I devised an air gap between the two layers, and actually it's open on both sides. So there's a little stream of air going past, and I'm hoping that the condensation won't fall onto the insulation. We'll see in 5 years' time, but that was the building physics which allowed us to do that. Wouldn't be the model to do that. So similarly, if you looked at the wall insulation, this one's got a number of layers: WeatherTex, an air gap, insulation, plasterboard, framing. Now in the model, you can then represent that. So here's the representation of the construction in the model. 4 layers: weatherboard, air gap, insulation, plastering, gypsum plaster on the inside. The thing to kind of think is, to look at is that here I've ticked this box here saying that the insulation layer has been bridged by hardwood. So actually that insulation performance is going to be derated by the timber framing, right? Anyway, each of those materials, like for example, weatherboard, comes with all the conductivity, specificity, density, all the thermal performance values, all the solar and visible values, all the values that you would use for daylighting calculations, embodied carbon values, and other values as well. There's green roofs, phase change materials. You can put all of that stuff in there. So, you know, again, it's not a CAD model. It's a very physics-based model. And then, of course, we can calculate what is the thermal resistance and the thermal transmittance for these constructions. You can see here that this construction has got an R value of about 2.2, but when you derate it, because of the bridging, it comes down to about 1.7. So that's the number you want to use in your simulation to try and get the practical outcomes coming from there. And again, just to double check, that's weatherboard, air gap, insulation, and plasterboard there. Okay, so I've got my model represented. I make an energy simulation run. I run it for the month of July in winter. And I do what's called a free running run. So there's no heating, no cooling, all the windows are closed, it's winter. And what do I get out of that? Okay, so the green line is the outside temperature in Eastern Sydney. And you can see we never really get to zero. This one is about 2 degrees centigrade. Even that's a fairly rare occurrence. This is, you know, a representative coldest month in July. I've got 2 days which are sort of below 5 degrees, or 2 nights when it's below 5 degrees. And the takeaway message for me from this analysis is 2 things. One, the red line and the blue line are not too far apart, and that's the air temperature and the radiant temperature. So what the thermometer measures is air temperature. What I feel is radiant temperature. And what it's telling me is that they are not too far apart, so my design is reasonably robust. If there was a big difference between the two, then I'd start to worry, okay? And what's even more interesting is that the radiant temperature, what I feel, when it's the coldest part of the night, is actually a little bit warmer than the air temperature, which is a good design, right? The second takeaway is that when it's really quite cold, 2 o'clock at night, my room, that space is traveling around 12 degrees centigrade. So there's a 10-degree uplift by the fabric, which I'm able to capture. So what I'll do is next, I'll take that information, stick it into an Excel sheet, because I've got some criteria that I want to test, okay? I'm suggesting to myself that I feel comfortable if the space temperature was somewhere between 19 and 26. It's a daytime zone, so I only want to use it between 8 o'clock and 10 o'clock, and I'm interested in the performance at that time, okay? So from those hourly numbers, I'm saying, okay, there's 434 hours that I'm interested in, and I can see that there are about half of that time is comfortable without me doing heating and cooling, but half of the time is uncomfortable. So I need a small heating system to offset that load. Now I must tell you, I mean, we had, you know, visions of, you know, lifting the roof, opening up the north side, getting the sun in. All of that went away as soon as we started to see the budgets for construction. You know, we're professionals, we're not super rich. So it was like, okay, how can we take a box and make it look good and just get what we need to be comfortable? And I'm sure there's a lot of people, you know, doing something fairly similar on that. Anyway, that was winter. Now summer is different. You know, I started to look at the summer, and we know these things. I mean, the building physics tells you all these things. All of a sudden, the sun is high in the sky. Where the roof ridges were a problem in winter, they're no longer a problem, right? And in the afternoon, when you don't want the sun, you start to get big patches of sunshine come through those western windows. Remember, I showed you those western windows in the beginning. Okay, so I do something fairly similar. I make a model, make the model run for a summer month, and I look at the week, a summer design week, and try to compare the runs when I've got 2 options. Okay, so I want you to look at the bottom graph here. The green line is the outside temperature in Sydney's east. And you can see here, you know, Sydney, we really very rarely get about 30 degrees. Here's a day at about 34 degrees. Otherwise, we've got days at around 28, 29. There's another one there about 31 degrees centigrade. That's the green line. But if you look at the top graph and you look at this red line, that's the solar radiation coming through those western windows. And you can see that every one of these days after 12 noon, after the sun swings over to the west, you suddenly see this huge injection of solar radiation energy, solar energy brought in by the sun. And the response to that injection of solar radiation turns up as the mean radiant temperature in the space increasing suddenly. Okay, so what I feel in the space, my space starts to cook because sun comes in through the windows. You know, that heat, shortwave radiation comes in, hits something, becomes long wave radiation or infrared radiation. And that's not opaque to the glass. It travels out much more slowly. So I start to store heat, right? And that's why it's predicting that even on mild days, I might really get some really warm temperatures in the room. So your obvious design response will be, well, my obvious design response will be, I got to cut out that solar radiation. So in response, I schedule a blind. Okay, and I say, okay, I'm going to put a blind in, and that blind is going to cut out the solar radiation from 6 o'clock in the morning to 10 p.m. I just want to see what will happen if I do that. And the blue line on the top is what I've done there. Put an external blind, which will cut off the radiation during that time. And when I look at the mean radiation temperature, you can immediately see what it does. I've got an 8-degree drop in the mean radiant temperature because of being able to cut out the solar radiation from those Western windows. Okay, and you can see that happen all through the week. So there you are. I've got a design decision to say that, well, if I can, you know, maintain the radiant temperature to be around the 30-degree mark for most of that worst week in my house, I probably don't need an air conditioner, because for me, I can handle heat. I can't handle the cold, but I can handle the heat. So that was my design decision. And we went out and bought motorized Venetian blinds. Okay, I apologize for the picture. I went to my neighbor's house when it was on sale and I got it off the, the balcony there. But I can lift it, and I chose Venetians because I can control daylight and because I can control natural ventilation. Okay. Now, how do I look at natural ventilation? You remember I showed you that picture and I said, I'll come back to you. So here it is. So when we did the initial design, our garden faces south. And in Sydney, if you've got a garden and you've got a space, you want a big door, a glass door, which can help you to look out in the garden. That's fairly typical for us. So we have one here, south facing, unfortunately, or fortunately, whichever way you look at it. But I've got now the east elevation where it's going to overlook the neighbors. Now, I don't want to see him. He doesn't want to see me. So we put some daylight windows on the top. But we also make 1/3 of those windows louvers, which I manually operate. Okay. And then on the west elevation, in Australia, we have this beautiful thing called double hung windows, which you won't find anywhere in Europe because they leak. Okay. But they're great because they don't swing in or out. And when you've got a tight site, they're very good. And you can open them. When you open the bottom, you open the top, you get passages from which you can encourage natural ventilation. Okay, so the idea was that in summer, you could open these windows, open those louvers, and maybe open the south-facing sliding door and give yourself a natural ventilation flow. So I tested that, okay? And here I have 2 hours for which I have visualized that, and you can see how it works, okay? Now, to build that into the model, you need to put in a lot of information, okay? Which windows are openable? When can they be opened? What is the criteria by which you're going to open them, you know? If you've got an automated system which will allow you to look at the outside temperature and the inside temperature and take a temperature differential and then open the windows, go for it by all means. If you don't, well, then you got to think about how are you going to use this house in practical operation. And for me, it was like, okay, on summer days, I'm just going to do a whole month and see how it allows me to work. And those temperatures that I calculated, which I showed you, include these operable windows. And they're open. I think I've closed it in the heat of the day between, I believe, 10 a.m. and 4 p.m. I've closed the windows, but the rest of the 24 hours, the windows are open. I'm just trying to test how these this might provide an output. Now, in this particular picture, it is actually a little bit interesting, and I wanted to spend a couple of minutes on that. And that's because you can see that the airflow is coming in from these higher windows and leaving through the lower windows and from the open sliding door. Okay. Now that's not how you normally show natural ventilation happening. Normally, if you draw an arrow, you would draw the arrow from the lower window to the upper window, because you are thinking that all the natural ventilation takes place due to buoyancy flows. But if you go and take the subject that Professor Lena Thomas teaches you in sustainability at UTS, she'll tell you that those are arrows of hope. Okay. The second sentence behind that is that wind wins. Whenever there is even the slightest breeze, it overpowers the buoyancy flows, and that's then driven, the natural ventilation then becomes driven by the wind. So this is a real perfect example of that. Depending on the wind direction, here's another one. You may get flow in that way. In this case, the wind direction is such that the bulk of the flow is coming in from the big sliding door and exiting from the top and the bottom. Okay, and you can see the times here. You can check that out. This is not a CFD. This is just a visualization of what we call the airflow network. The models that we are using have got a heat balance component and an air balance component, or a mass balance component. And when they both interact together, you can get fairly interesting outcomes. Now, having done the simulation, I'm interested in how does it work. So here we go. I did did the same thing that we did for winter. I'm looking at how does it work for summer, and I'm saying, okay, I can sort of bear up to 28. If it starts to get beyond 28, then things are going to become pretty uncomfortable for me. So how many hours does it sort of get beyond that number? I think I've done this for January. Yep, there you are. So if I'm looking at just the air temperature, 6% of the time, that's not too bad. I can handle that. Okay. But if I start looking at the radiant temperature, then the story changes a little bit. About 40–45% of the time, it's pushing into the uncomfortable area. Now, the reality is going to be somewhere in between. Because why? Well, I'm using one particular simulation year where the data, it's not going to be the same. The way I use the building is not going to be exactly the same every day. It's going to be different. Some days are going to be worse. Some days are going to be bad. I have seen that if there are 3 or 4 days, hot days in a row, then it can get quite uncomfortable. But that's fairly uncommon in Sydney. So at this point, the decision has been, we don't put an air conditioner. We have a small heater. That's sufficient for us. And the reality from observation has been exactly that. We've got a digital thermometer in the room. We rarely drop below 16, 15 degrees on a really cold night without any heating and cooling. We rarely get up to 28, 29 degrees. Last year, about 3 times we got up there. And that was a 36-degree day. And actually there were 3 days running about 32 degrees when it sort of did that. The back of the house is cavity brick. That's about 5–7 degrees cooler. So you just migrate I don't know how long that'll happen. With climate change coming along, we may have to change our decision, but for the present, that'll do, right? Okay, so just to sort of finish off on this case study, that's what it used to look like, and that's what it looks like now. And there's my air conditioner. There's a ceiling fan there. And then, of course, my natural ventilation strategy is the west-facing and the east-facing windows and this sliding door. Okay, so we're going to leave that there for the present. When I was building this presentation, I suddenly realized that I haven't talked about energy at all. You know, I'm talking about all kinds of things to do with modeling, but I've been talking about daylight and sunlight and natural ventilation. So I thought I should show you a little bit about how we do energy simulation for, or how we've used energy simulation for looking at energy use in the building. So here's a, you might say a typical suburban home, 2 floors, 3 or 4 bedrooms in, I won't even tell you what suburb it is in, but anyway, we had modeled this for a client, and typically we do large buildings, large air conditioning system, control systems, select all kinds of fancy glass, shading devices, all that, and then look at control strategies, etc. This is new for us because one of our colleagues is very passionate about passive house and housing design. And so we've been doing a series of consulting projects on that. So on this house, we put in all the right bits and pieces. You know, so we've got insulation on the ceiling. There is insulation on the walls. We've selected fairly decent windows, 2 types of windows. So the windows on the ground floor have got a different performance to the windows on the top floor. The client hired an architect. They brought the design to us. We optimized it, or we changed it to kind of resolve things to it. And what we did was, initially we started off by saying, okay, let's model what happens when we predict heating energy use across the year. So here's the annual energy simulation run, okay, for a building like that. And what we did do is that we looked at data on how a typical Australian house leaks in terms of air infiltration. And if you don't understand that term, there's a 1-hour lecture I've done called Energy Simulation, Introduction to Energy Simulation. It's on the Design Builder software website. You'll find it. You can have a look at that. And one of the loads in the building that, you know, adds to the heating load is how much a building leaks. Now, I was telling you my colleague's quite passionate about passive house. And one of the things that passive house does is it's a European standard, so they're very keen on reducing heating energy use. And there is an impact to air infiltration that, you know, in Australia, we don't really think about a lot. So we did a number of runs, and I'm just showing you, you know, the final outputs. We did runs at 15, 10, 5, 3, etc. And we sort of said, okay, if you can get the house to 3 air changes from this 15 air changes by employing strategies to tighten up the building, right? Where do we go from there? And so you can see here, we predicted that you were using about 20 kilowatts of heating at the typical 15 air changes per hour leakage. By the time we got it down to about 3 air changes per hour, now you've got to do things to the design to make it tight. Okay, you got to look at all your joints. You got to put in a wrap, a barrier, a vapor permeable barrier. You got to look around the windows. How do you install it so that they don't leak? All the joinery, all the gaps, all the switches, you might need to put, you know, you don't think that switches will leak, but on a cold day, if you put your hand near the switch, you'll find that it leaks like crazy. Any of the joinery that, say, for example, in your kitchen, you'll have holes for the drains to go out from it. They have not been blocked off, you get a lot of infiltration coming from that. Okay, you do some of those things and you've gone from 20, you've brought it down to about 13 kilowatts. Okay, that's step number one. Step number two is you go, well, once you've tightened the house, there are some unexpected consequences. Okay, you have moisture in the house. In a leaky house, the moisture disappears because it leaks. But in a tight house, the moisture stays there. And you might start to build up mold. Okay. In a leaky house, you don't worry about carbon dioxide concentrations. In a tight house, particularly in a bedroom at night when you close the door and go to sleep, the CO2 concentrations inside that room will start to increase. So from Europe and the US, we've had what are called heat recovery ventilators. Okay, so what you've got is you've got a little heat exchange box. You supply fresh air, outside air, to the bedrooms, to the living rooms. You extract polluted air with moisture from the bathrooms, the toilets, the kitchens, and then the magic box exchanges the heat. So in winter time, the cold air that you bring from the inside goes past the heat exchanger, picks up the heat from the air that you're exhausting, right? When you do that, by just using the heat recovery, you bring it down from a peak of 13 kilowatts down to 9 kilowatts. Okay, so all this is from the models. You can test these sorts of things on your models. So if you then took a summary of what we did, what we are saying is that for heating energy use, right, in Sydney, by the way, we got rid of about 3/4 of the heating requirement by doing what we just did. The size of the equipment that you need, and by the way, there's a difference between thermal energy and what you need as electricity to give you that thermal output, okay? That's when air conditioning sort of comes into the picture. But anyway, you've gone from your requirement of 20 kilowatts of heating down to about 9. So the capacity of your system in terms of electrical energy has gone from about 7 to 3, more than a 50% reduction. Now that's for heating only. Okay, you've got to look at cooling as well. And again, there are where you have to combine what you can do with natural ventilation and what you can't do with natural ventilation. The problem with cooling is, of course, that you need the cooling on the worst day. Okay, so even if you did all the strategies for natural ventilation, etc., if you put the system in, the system's got to handle the worst day. Now, one of the things that we've been trying to tell clients, very difficult to get them to understand that, is that you can actually undersize your system slightly so that on the hottest day when it's 36 degrees outside, you don't need to be 24 degrees exactly on the inside. You could be 26 or 27 and that'll still work, okay? And that kind of thing you can test on a model. You can deliberately undersize a system and see what is the conditions within the spaces. Those are, so I'd be saying that, you can use these sorts of models in very sophisticated ways as long as you know the question that you want to answer. I'm going to leave it at that. I think we've just about crossed our 45 minutes and take any questions that we might have.
Super. Thanks so much, PC. That's fantastic. Before we kick off the discussion, maybe I'll just start off with a question. So if anyone has any questions from the audience, please feel free to post them in. We did have a couple come in while you're presenting. So you probably can read them, but I'll read them out loud for the audience as well. So with regards to the analysis of the useful daylight, to what extent does the surrounding context and specifically the trees affect the simulation?
Okay. So again, I think it's about the question that I wanted to answer. You've noticed that in the model, I did have the neighboring buildings in there. So the effect of the neighboring buildings is included. Now, there weren't sufficiently, there weren't too many trees in my backyard that would really affect the amount of daylight that I was getting. So I wasn't really that interested in putting in the effort to make the model or include those trees in the model. However, if you wanted to, you could put that into the model, and it would allow you, it would give you the effect of the trees. My design decision didn't really require me to add the surrounding trees in there. But that's a good question.
Superb. And another question is, how crucial is the weather data for the simulation? So if we had the weather data if we didn't have the weather data for a specific spot or for the specific site of your building or projects, do you have any recommendations about choosing the weather data for the simulation? So I'm guessing if you don't have the weather data available for that specific site location, what is the next best thing?
Okay, again, it's a great question. Now you got to remember that your simulation works best when you are testing design A against design B, right? Your simulations are not reality. They're a facsimile of reality. So by doing a simulation and saying that, oh, it's going to get within X% of that, it's not going to happen, right? So when you do, if you look at the weather data that's available, you'll find that there'll be one file for all of Eastern Sydney. There's one file for Western Sydney, and that's about as much as you will get, right? So again, you're getting a reference weather file, and the way that people build reference weather files is they look at about 10 years worth of data, and then in some ways, in some weather files, they'll pick the most representative months for each of the months from those 10 years and build kind of a mixed weather file which represents that climate. But essentially what you're trying to do is to say that overall, how would your design respond to that weather file? Okay. Now, if you've been following LinkedIn, you'll notice that Cyro has just put out, I think it was 2 days ago, a bunch of curated future weather files. Fantastic. Okay. Allows me to then look at my model, test it for what it is doing today with a file for today, run it through a 2030 file to say, well, what would happen if the weather sort of changed in the way that it's predicted. So these are tests that you're doing. I would say as long as we understand the question we're trying to answer, use it that way. But don't think that what you're doing is going to be exactly represented in the reality. It's not going to happen, right?
And then one more question that just came in. Of course, firstly, incredible data analysis approach to the residential design. How do you strategize if a skylight is to be included in a space, and how would it impact the thermal and daylight factors of the house?
Okay, good question again. Thank you for that. Now, as I said, if I was keen to understand that, I would have built a model including the daylight, the skylight in there, and then redone the simulation to see what the impact was that, okay? Now at the time, and I'm not even sure that at the present in my model, I can do what's called a tubular skylight, which is what I installed. The tubular skylight actually is pretty good in a thermal sense. It's got a glass dome on the top, and it's got a diffusing panel on the bottom, and a very highly reflective tube all the way through. In terms of if you look at the area of the roof, and then you look at the daylight, the tube area, it's a very small fraction. So, in practice, that's not going to be a deal breaker. Okay, but if I had many of them, and then I wanted to account for them, certainly I would be putting those back in there, putting an infiltration rate for them, an air leakage rate for them, putting a U value for each of the materials in there, and then working out what the heat loss and the daylight change would be. But as a design decision for what I wanted to do, I'm taking the picture to the client and going, look, you got a dark spot there. If you want to not have that dark spot and want to avoid switching on a light the whole time you're in the kitchen, that's a place where I should be putting in a skylight. Okay, that's what you want to do, right?
And then another one. So how much consideration should be put into building materials? Can a well-executed sustainable design offset poor thermal materiality choices?
Whoa.
These are some really hardcore questions here, and they're fantastic, actually. Yeah, yeah. So it's 6 p.m. PC. Who would have thought to be answering philosophical questions at this time?
I think I need my glass of red to start answering these questions here.
No, but I think that's a really good one, because I think that's a thing that we usually kind of hope that the optimization process is going to solve for us, but the slightest change in the material surely has an impact.
Oh, that's the thing is that if you have a look, I mean, and again, I would say, let me go back to Passive House. They have 5 design principles that they talk about. And, I need to sort of maybe moderate that to say that those 5 principles are extremely good for heating climates. For cooling climates, you probably want to do a little bit more than just that. But one of the things to think about is that once you insulate a wall, so if you go from an insulated wall, from an uninsulated wall to an insulated wall, even if you just put a small amount of insulation, you get a huge benefit. But then if you start increasing the amount of insulation, you get a marginal benefit, right? So somewhere you want to kind of say, well, how much should I put? And that then becomes a kind of a conversation between what does the code want me to do, right? What can I fit into the construction without having to change my construction detail? Like we build, framed houses, timber framed houses. You've got a reasonable space in that frame. So how much can you fit in that? If you put in more than that, you're going to compress that insulation and you're going to lose the insulation value anyway. If you use the entire gap for the insulation, then you don't have a breathing space. You want a vapor barrier. You might, in the case of our wall, we had there's a weather barrier, which is actually a waterproof barrier, but it's vapor permeable, right? And then you want an air gap behind that. Then you want the insulation. Then you want the plasterboard behind that. So it becomes that, is it only insulation that you want? No, you actually want to then think about the window performance. You want to think about the air tightness performance. You want to think about how the house is going to respond in summer and in winter and in the middle seasons. And you want to have a kind of and that's what you call optimization. Where do you put these things together so you get the best result overall? Now, can you avoid having artificial heating and cooling systems? I would say that's pretty difficult. You need, if you did a fully solar passive design and you had the land area to do it so that you didn't have obstructions, and you built a really massive wall and insulated it and you charged it during the winter, that kind of thing can be done. But in modern, you've got a semi is 7-meter wide plot, 50 meters deep. What can you do in that? That's a different kind of, much more practical sort of a thing to do, I'd say. Yeah.
Fantastic. I'd like to maybe open up for Dave, and then we'll kind of end up on that. I know Dave is kind of teaching a studio in which they're using kind of a very similar methods, but on a similar scale to what you've been doing. So Dave, over to you.
Thank you so much, PC. This is fantastic. Exactly what we were hoping for. I'm really curious. Obviously, this is a very high investment model to make in the first place. And as you said, you're very much testing a design that exists and answering very specific questions. Do I need air conditioning? Do I need heating, etc.? What kind of level of insulation within an existing wall? I'm really interested in and you've already said that the simulation, the software is really going rapidly, that there's things you can do today that you couldn't do even 5 years ago. I'm really curious about how, what is the cutting edge in terms of building feedback loops of optimization of things where, to take the example we've spoken to, where it would decide to make the window a little bit smaller or a little bit bigger, or that these kind of things would be, what is the state of art in terms of optimization, and what's your feeling around that? Is it still better to do a very managed, because you know what you're doing, and do 5 simulations with very clear objectives and make your comparisons, or are there people successfully doing full feedback loop automated optimizations?
A bit of both, actually. Like, I'm much more of a rifle guy, because I must say that because I got domain knowledge, I can take 5 shots and get to where I want to, right? But, you know, Energy Plus, for example, has got a genetic optimization algorithm built in. You can pull a couple of parameters and go, right, as you said, exactly, you know, move your windows from 10% to 80% and work out 1 or 2 variables, and it'll do the runs for you. In fact, I think if you go to the Design Builder website, they've got a whole webinar on optimization, and you're looking for that Pareto front where you've got a few variables and you're looking at that. I think for the building fabric, that's actually quite doable. There's enough knowledge within, you know, and the variables that you're testing are amenable to that, right? When you start looking at systems, HVAC systems in particular, that is a much more difficult thing to do to get a real useful result. I mean, I've seen lots of simulations where they, you know, but the problem is, you know, you're dealing with chillers, boilers, fans, controls, you know, humidity of air, you know, latent loads, sensible loads. Each system works differently, responds differently. You change 1 bit on it, things move differently. There are limitations to how you drive chillers and boilers and fans, and the systems don't always do that by default. You as an engineer have got to take that decision, right? But on the fabric side, I think, you know, those decisions are simpler to take. You can take 2 or 3 variables and get it to crunch through, right? Can you automate geometry? Yes and no. I think if anybody recalls using Ecotech many years ago, Andrew Marsh was a monster in terms of simulation. You know, he could, I think he's probably written one of the few engines which could actually design an overhang for you if you said, okay, I only want the sunlight to come in during this time to this time in a year. That's, you know, that's heavy duty stuff, right? Most models can't do that. You've got to think of what it is you want to test, and then devise the optimization routine, and then get it to do what you want. You can certainly do that, you know. You're beginning to see, for example, within Energy Plus, you can attach Modelica bits to it. And Modelica is a very flexible mathematical language, so you can do stuff with it. Within Rhino, you've got Grasshopper scripting, you know. It's got Energy Plus built in the background somewhere. I think Climate Studio is coming up with Climate Studio daylighting is really quite good, but the thermal is still, it may get better across the years. But right now, I would say that, yeah. So I think definitely options available, but it is a little bit of a case about learning to walk before you run. So I mean, you can, I would be suggesting maybe get a simple shoebox model, get a simple optimization algorithm going, see where you can push it to, and then go off and start doing things that are more complex and crazy.
That's a fantastic piece of advice, to be honest.
Sorry?
That's a fantastic piece of advice, to be honest, kind of working at a bit of a abstract thinking, higher level thinking, trying to figure out how it works before really being able to look into the much higher level detail, which, as you mentioned, is tremendously challenging. You have so many moving parts, so many variables, so many specifics that would be quite challenging to simulate. Right, I'm quite careful of the time. Not that I want this to end, but we did promise people and you that we would end at 6 o'clock. And so I want you to go back to your nightly life in your beautiful garden and enjoy your thermal cooling. We really appreciate your time, PC. So for those of you who are in attendance, PC has kindly allowed us to record the lecture and post it. Once we have it online and we have the link, we'll share it with you. I'll get the attendees list, and we'll just email all attendees who have attended today, and we'll also post it on LinkedIn and the university's school's Instagram account. But until then, if you can all join me to thank PC and Dave for setting this up, we really appreciate it. And yeah, we'll see you all in the following lectures.
Well, thank you so much for the
Thank you so much,
opportunity, guys.
PC.
No worries.
Thanks so much. All right. Well, have a safe rest
Lockdown
of
evening.
August. Yes, exactly. Everyone stay indoors if you're in Sydney, and we'll see you all very soon. Goodbye.
Bye then.
Bye. Thanks.
Thank you. Good night.